Okay, so this is a question from JAM 2021 mathematics exam, and it's a question number 18. Question is, consider the function f of x is equal to function is defined as 1 for all irrational points, right? And also at 0 the function is defined as 1, and the function is defined as 1 minus 1 by p for all rational points, right? At irrational points, function is defined as 1. Also at 0, function is defined as 1. And at all rational points, function is defined as in this way 1 minus 1 by p, right? Where this p is the denominator of that rational point, right? P is the denominator of that rational point. Okay, so to solve this problem, we will prove some claims, right? So my first claim is f is not continuous at all x from set of rational numbers. So to prove this claim, we will use one result, and that result is f is said to be continuous at a if and only if every sequence uh, every sequence xn converges to a, then sequence f at xn converges to f at a. Okay, that means if this statement is true, if every sequence xn converges to a, then sequence f of xn converges to f of a, then we'll say that f is continuous at 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 a, right? That means if sequence xn is converging to a and we are getting that sequence f of xn, f at xn, it is converging to f at a, then we'll say that f is continuous at a. And vice versa, if f is continuous at a, then every sequence converging to a, what we'll have, sequence f at xn, it will also converge to f at a. Okay, so we are going to use this result to prove this claim, right? That f is not continuous at all x belongs to set of rational numbers. Okay, so let let a be an arbitrary rational number. Okay, let a be an arbitrary rational number. Okay, so I'm writing a as, we can write a as n by p, right? Where n is from set of integer excluding 0 and p is from set of natural number, and GCD of this np is 1. Okay, so f at a, which is n by p, so it is 1 minus 1 by p, the way our function is defined. Okay, now what I'm doing, now let xn be a sequence of irrational numbers. Let xn be a sequence of irrational numbers converging to a. Okay, because we know that uh, between any two real numbers there are between any two real numbers there exist infinitely many rational and irrational numbers, right? So that's why it is always possible to choose sequence of irrational numbers which is converging to a, because of this fact that between any two real numbers there are infinitely rational and irrational numbers. Okay, because of this fact we can always find sequence of irrational numbers, right, which is converging to a, okay. So I'm saying let xn be a sequence of irrational numbers converging to a, right? Therefore f at xn, because xn all the members of the sequence are irrational numbers, and at irrational numbers the function is defined as 1, right? So f at xn it will be 1 for all n belongs to set of natural number. Okay, and f at a, what we are having 1 minus 1 by p. Okay, so what we are seeing over here now, here xn is converging to a as n tends to infinity, but f at xn does not converge to f at a, right? Why? Because uh because this value is what, 1 minus 1 by p, right? And this is not same as 1, and it is less than 1. That means I can say that this sequence f at xn, it is not converging to f of a, right? So we got here. Okay, so here we got a sequence xn which converges to a, but sequence f of xn does not converge to f at a, right? Therefore by that result f is not continuous at any rational numbers, right? At any rational numbers. Okay, in fact f is not continuous at a, right? And here this a is any arbitrary rational number, so overall we can say that f can't be continuous at any rational number. Okay, so our first claim is proved. Okay, now we are going to prove our next claim. My second claim is f is continuous at all x from set of irrational points. It is continuous at all x from set of at all x which is from set of irrational numbers. Okay, so again to prove this claim I'll use the same result, this one. Okay, so let's start proving this. Okay, now again I'll consider any arbitrary irrational point. So let x, I'll take x, let x be an arbitrary irrational irrational number, right? Therefore f at x, it will be 1, right, the way our function is defined. So now again, I'll consider a sequence which is converging to x. Okay, so let xn, so first of all I'll consider a sequence whose all members are irrationals, and that sequence is converging to x. Okay, so let xn be a sequence of irrational numbers converging to x, right? So x is there, so I'm considering a sequence of irrational numbers, right, all irrational number which is converging to x. Okay, so here f at xn will be 1 for all n. Also f at x is 1, right? So here we get xn is converging to x as n tends to infinity, and f at xn, it is also converging to f at x. Therefore from result, right, from result f is continuous, at x, right? F is continuous at x. Okay, but see, x is any arbitrary irrational number I have taken, and I have considered a sequence of irrational numbers which is converging to x. So there are not only sequence of irrational numbers which is converging to x. There may be a sequence of rational numbers also which is converging to x. So now we'll consider a sequence of rational numbers which is converging to x, and then we'll see whether f at xn, whether this sequence f at xn, it is also converging to f at x or not, right? If it will not converge, if this sequence f at x, if this sequence will not converge to f at x, we'll say that f is not continuous. F is not continuous at x. In fact, what we require any arbitrary sequence, right? What we require any arbitrary sequence converging to x, such that f at xn it is also converging to f at x. Then only we can say that f is continuous at x. Okay, if we can get a sequence which converges to x, but f at xn, but this sequence does not converge to f at x, then we'll say that f is not continuous at x. Okay, so just now we had taken a sequence of irrational numbers which is converging to x, and also we got that sequence of this sequence f at xn, it is also converging to f at x. So from result we will say that f is continuous at x. Now let's consider. Okay, so okay, wait, I'll not say this thing, just here. First of all, next we will consider a sequence of rational numbers which is converging to x, and right, and then we'll check whether this sequence f at xn, it is also converging to f at x or not. Then combining this result and that result, we'll say that f is continuous at x. Okay. Okay, now let xn be a sequence of rational numbers converging to x. Okay, now I have considered a sequence of rational numbers which is converging to x. Okay, now since we can write x as, because x is irrational number, so we can write x as a comma x1, sorry, a comma, say y1, y2, y3, y4, and so on, right? Where this a is integral part of that irrational number, integral part, right? And all this y1, y2, y3, they are all the decimal numbers. They are all the digits after the decimal, you can say. Okay, so I'll write where this y1, y2, y3, they are from this set. They are from this set 0 to 9, right? All this y1, y2, y3, y4, y5, and so on, they will be number from this set, right? They will be number from 0 to 9. Okay, so we can write any irrational number in this form. Okay, and again further it can be written as a plus 0.y1, right, plus 0.0y2, right, plus 0.00y3, and so on. And this further can be written as in this way: a plus y1 upon 10, y2 upon 10 square, y3 upon 10 cube, right, and so on, right? Now let x1 is equal a, x2 equal a plus y1 by 10, x3 is equal a plus y1 by 10 plus y2 by 10 square, and so on. Okay, and notice all these are rational numbers, right? All are rational numbers. And as okay, so xn I can write it down as a plus y1 by 10 plus y2 by 10 square, right? The last term will be yn minus 1 upon 10 to the power n minus 1, right? And notice that, and as n goes to infinity, xn will converge to x, right? As n goes to infinity, xn will converge to x, right? And f at xn, okay. Okay, uh so as n will goes to infinity, xn will converge to n. Now f at x1, so what is x1? Our x1 is a, so a is integral part, that means its denominator is 1, right? So f at a, and a is rational, it is rational number also, so the function is defined as 1 upon 1 minus 1, that is 0. Okay, and f at x2, it is, so x2 is a plus y1 by 10. Okay, so it is another rational number. Okay, and if you solve it, so you will get its denominator is 10. So f at this point, it is 1 upon 1 by 10. Okay, you can check it. So f at x3, f at a plus y1 by 10 plus y2 by 10 square, and it is 1 by 10 square, and so on, right? Sorry, and so on. F at xn, you will have 1 upon 1, 1 minus 1 upon 10 to the power n minus 1. Okay, and limit n goes to infinity, f at xn, this is limit n goes to infinity 1 minus 10 to the power n minus 1, which will be, it will be 1, right? This 1 is nothing but the value of f at x. Okay, and this means that f at xn, it is converging to f at x as n goes to infinity. So let's say it is star, and it is double star. So from star and this double star, we get as xn converges to x, and just notice this sequence all the members of the sequence is rational number, right? So we get as xn converges to x, f of xn converges to f of x, right? As n goes to infinity. So we considered two types of sequences converging to x. One was rational sorry one was sequence of irrational numbers, right, which was converging to x, right? Xn was sequence of irrational numbers converging to x, and we also saw that in that case that f at xn, this sequence, it is converging to fx. And also we consider another type of sequence in which the members of sequence were uh, rational numbers, and it was converging to x. In that case also we got that f at xn is converging to f at x. So overall we can say that, and now this I'll say 2, right? So in 1 I took the sequence of irrational numbers which was converging to x, and we got that the sequence f at xn, it is also converging to f at x. Okay, so from 1 and 2 we can say that from 1 and 2 we get that any sequence, whether it is sequence of rationals or irrationals, we get that any sequence xn converges to x, we get we have sequence f at xn converging to f at x, right? Therefore f is continuous at x, right? And this x was arbitrary irrational number, right? This x was arbitrary irrational number we had taken, irrationals, right? This implies f is continuous, that so if it is continuous at any arbitrary at if if f is continuous at any arbitrary rational irrational numbers, so it means that f is continuous for all irrational numbers, continuous at all x from set of irrational numbers. Okay, now our next claim is third claim, f is continuous at 0. Okay, now I leave this to you guys to prove it. Okay, so this will be the homework. Okay, okay, now let's come to the our problem. Okay, so second option is f is continuous at all x belongs to set of rational numbers. So just in claim 1 we proved that f is not continuous at all x belongs to set of rational, so this option is wrong. Say C option is f is not continuous at all, okay, but f is continuous at all rational irrational points, so this option is also wrong. And third claim is f is continuous at x equal to 0, so this option is also wrong. Okay, so now the remaining, so all three options are wrong, so only A is true. And why A option is true, you can easily check it. So what is option A? All x belongs to set of rational excluding 0 are strict local minima for f. Yeah, just see that, because at the rational points the function is defined as, at rational points function is defined as 1 minus 1 by p, right? And at irrational points function is defined as 1, so definitely 1 minus 1 by p is less than 1, right? And just know this fact, if a is any irrational, sorry, if a is any rational point, right? So at a So at a, suppose a can be written in this way, right? So at a, at this rational points, the function will be 1 upon 1 minus b. But in neighborhood of this a, there are infinitely irrational points, right? That means in neighborhood of a, and at irrational points the function is defined as 1. That means in the neighborhood of this a, the value of function is what, 1, and this 1 minus 1 by p is definitely less than 1, right? Because this p is positive, because p is from sort of natural number, right? So p is positive, so 1 minus 1 by p is definitely less than 1. So that means all x from set of rational numbers excluding 0 are strict local minima for f. So option a is true. Okay, thank you.